Welcome to this series of videos where we are going to be explaining how to perform flexibility workflows using the Flexibility Hub inside Scipion. In this second video, we will be covering some of the different possible options that we have in order to estimate conformational landscape starting from particles and in some cases other data types like for example volumes or structural models. Okay, let's start seeing the different options that we have available in this workflow. In this workflow, we have run three different types of software. First one is the CERNI 3D, which belongs to the family of the CERNI 3D workflows, which mostly try to estimate conformational landscapes through the estimation of deformation fields, which is a way of understanding how a molecule tries to move from a reference state to all the different states that have been captured by our particles. The next one is Hetziner and CryoEM, which are software that work in a slightly different way compared to the CERNI 3D family programs. In these programs, we are not trying to estimate the deformation field, but we are trying to estimate directly the density, the CryoEM density map that will allow us to get different states based on the information stored in the particles. Let's start first by having a look at the CERNI 3D. You have two different ways to access the form of this protocol. One is, for example, clicking in Ctrl F, and you will open this search dialog where, for example, you can look for CERNI 3D. And once you do this, you will see all the different protocols containing either in the protocol name, the help, information about the CERNI 3D. In our case, we are looking for the CERNI 3D, so we can try to make this bigger and look for CERNI 3D angular line. The other way to access these protocols is to go into the Flexibility Hub view in the Scipion, then go to Landscape Estimation, and go into the family of programs estimating deformation fields. And here you have the CERNI 3D family of programs. Here we have the classical CERNI 3D, which is not based on deep learning, it's based on a standard optimization. You have other tools for estimating flexibility based on map, structures, but here we're going to be using the CERNI 3D. So you open this tab, and you see two different programs. We're going to be focusing on the first one, which is the one needed to train and estimate or get an initial estimation of the landscape. And then you also have the predict, which is mostly used when you have already a trained network. Let's double click in the protocol, and now you will be able to see the form that you need to fill up. Let's click Advanced just to see all the different options. So the first tab you need to fill is the Input tab, where you need to provide your input particles. In this case are the particles you have imported in the Scipion project, but this could be your particles coming from flexible refinement, consensus, and so on. The reference type. This reference is the volume we are going to use as our initial state, which will be suffer the displacement of the deformation field we are estimating to approximate the different conformational states in the particles. This reference can be either a volume, which is the default option, or a structural model, in case you already have a tracing based on your map, or you have been able to download a structure from the PDB that you want to use. Here we will use the volume, and then you will be shown with two extra fields. The input volume, which is the reference map we're going to be using for this deformation or the application of the deformation fields, and then you can provide a volume mask. This volume mask is a binary mask, so it has zeros where you have the background and ones where you have the protein, and is mostly used for performance and accuracy purposes. This basically tells the algorithm, I want to compute my fields, my deformation fields, only in the regions where I have the protein, and I don't care what is going on in the other parts of the volume. So this is very, very useful. Usually we want this mask to be as tight as possible, but also it is interesting if it is possible to keep as much of the mass of the protein, because otherwise all those regions that are not present in the mask won't be taken into account during the computation of the deformation fields. The next parameter is a downsampling, which is only internal. So if your particles, for example, have a box size of 300 pixels, like in this case, you will output particles with a box size of 300 pixels, but internally, the CERNI algorithm will downsample them to this size. And the idea is that since the particles are very, very noisy, there is no need to really work with the full particles, because at the end, there is some information that is so buried in the noise that we won't be able to really estimate it. So doing this downsampling first concentrates more the signal, so makes the prediction more accurate and also makes things faster. Usually we use this value of 128. For example, if you have a larger board, you can go to 156. It will also depend on your GPU memory. You have more or less GPU memory. You can also play with this parameter in order to fit the data. Then we have the Cernic3D parameters, which are the degrees of the Cernic3D basis that will control how local the deformation field will be. So values here that are smaller will mean that you are able to estimate very well global motions, but not so well local motions. And if you increase the degree, you will not have an impact on the performance. Using this deep algorithm, in the classical one, you will see a decrease in the performance. But you will be able also to estimate more accurate fields, which means that in principle you should see smaller motions in your protein. But since our particles are very, very noisy, you have also a higher possibility of overfitting to the noise. And the last section are the CTF parameters. By default, we want to apply the CTF always. You can set this to no in case, for example, you are working with synthetic data or you have corrected already the CTF by some other means in your particles. And then we have two different ways of correcting the CTF. First one is the apply mode, which basically means that once the Cernic compute the theoretical projection internally that will be used to compare with experimental ones, you corrupt those projections with your CTF. And the other one is to keep the theoretical projections untouched and correct the experimental particles using a Beerer filter. We have seen that performance of these two is more or less similar, but you can get a slightly different result, so it could be useful to run this program twice and then go into the consensus step that will be explained in next videos. And the padding factor is just controlling the size of the images when computing the Fourier transform and applying the CTF in order to have higher accuracy. The network tab is usually not needed to touch it, has to do mostly with the type of architecture you are using when training your network. Also, if you want or not to refine the pose of your particles at the same time you are computing the deformation field, which is usually a good option, so by default is set to yes. And here you can control the number of training epochs, number of images in a batch, which this could be a useful parameter if you are running out of GPU memory. Together with the downsampling, you can either increase or decrease this number depending on your GPU requirements. The training fraction, which basically allows you to split into a training dataset and validation dataset. And this point step is controlling how many voxels in your volume will be used to generate the theoretical projection. So for example, a step of 1 means all the voxels will be used to generate the projection. And a step of 2 means that 50% of the voxels will be not used when generating the theoretical projection. In general, we will use all the points, but if you are seeing very, very low performance or you want to get things faster at the cost of having a little bit less of accuracy, you can increase this point step here to 2 or 3. The last tab is the cost function. So here you are deciding what type of cost function you will be using to train the network. By default, correlation is set, which is usually preferred because it's faster, but you can also use the Fourier phase correlation. In terms of performance, both of them are similar. In terms of the things you will get more or less the same thing with any of these two functions. But with the advantage of the Fourier phase correlation is that it's a bit slower, but you can apply a mask to the Fourier transform in order to exclude those frequencies that are very, very high, that most probably are mostly dominated by the noise. So you don't want to include them in the analysis. I will use this one when you are seeing poor performance when using the correlation. By default, correlation usually give you good results. Okay, so once you are happy with your form, you can click on execute, and the Cernic SUD will be executed. It will take some time, so for example here it took around 45 minutes. And once it finishes, you will get here in your output in a Scipion a set of particle flex. Let's see what this set of particles flex looks like compared to the set of particles that we input to the program. As you can see, in terms of information, they are very, very similar. They have sampling rate, CTF, and so on. But the things that are different in the flex particles is that at some point you have this very long vector here, which is the set flex vector, which in this case is a Cernic3D coefficient vector associated with this particle. So this is the one allowing us to recover the conformational state estimated, for example, for this first particle here, particle 1, which is not present in the input set of particles. So really, the set of X particles is just the same set as the input set, but extended with all information needed to recover conformational states according to different software. So for example, in the CERNIs, it will be the CERNI basis, parameters, the coefficient vector, and so on. If you run CryoDragon, you will get, for example, the latent space and so on. Okay, as a second example, let's have a look at the CryoDragon program. So the CryoDragon, in order to use it, you need to install the Scipion EM CryoDragon plugin. And once you have it installed, you will get here in the landscape estimation a new tab. Let's close this one for the deformation fields. A new tab called Heterogeneous Reconstruction, where you will have the CryoDragon section. And in the CryoDragon section, you have all the different protocols implemented from the CryoDragon pipeline. In order to train the CryoDragon network, you need to run two different protocols. The first one is the preprocess. This preprocess is just used to generate a set of particles that CryoDragon likes. So it is not really going to give you any kind of landscape, it's just kind of the preparation step in order to train the network. Here you can specify first the particles you want to use, whether you want or not to downsample the particles, and the reason for this downsampling is similar to the one used for the CERNIs, but here there is a small difference. In the case of the CERNIs, we can estimate our deformation fields on smaller particles, but these deformation fields can be still applied to the original particles. In the case of CryoDragon, if we put here a downsample of 128, it means that the maximum size of volumes that the CryoDragon network will be able to create will be 128 pixels. So if you want to create or to allow the CryoDragon network to give you much better maps, then you need to put here a bigger value. But you have to keep in mind that bigger values will mean that probably you will run out of GPU memory. So depending on your requirements, you need to play with this number. And the splitting chunks, it also has to do with how many splitting or how you want to split your data when doing this preprocessing. So it's more needed for memory issues purposes. So by default it's set to 0, which means no splitting. You fit all your particles into memory. If this works, it's great. If you see that you are getting errors, you can start doing splitting 1, 2, 3 until you see that the memory error goes out. If we click on the Advanced tab, you also see that we have an option to apply a circular mask. CryoDragon works in Fourier space, so this circular mask is similar to the one we saw in the cost function of the Fourier phase correlation. In the case of the CERNIs, is to exclude those frequencies that are very, very high, so they will contribute to noise, but not to the signal match. And then also to determine if your particles are white or not, just to invert the contrast. Once you are happy with your form, you can click on Execute, and you will get a CryoDragon particle set, which is not really usable in a Scipion apart from the CryoDragon pipeline. So this is just, as we said before, a preparation step. Once you have your preprocessed particles, we can go into the second step of the CryoDragon pipeline, which is the training of the variational autoencoder, which is this protocol here. This protocol form, again, is divided into 3 different tabs. The first one is the input, where you need to provide your CryoDragon particles, which is a set of particles created using the preprocess protocol. And also you can specify the latent space dimension, which will determine also the freedom CryoDragon has in order to define the conformational landscapes. Usually you put a number here between 8 and 10. This will be more than enough freedom in order to approximate very well all the different states. And then the number of epochs for the training. In the advanced, you can control all the parameters regarding the network. So, like for example, number of hidden layers or the nodes in the hidden layers in the encoder, also architecture of the decoder. And lastly, you have the extra parameters, which allows you to put here any kind of a string, like for example, let's say minus something 2. And the idea of this is that in a Scipion, we usually don't put all the parameters in the form, but we are trying to summarize the parameters that we are putting here to keep only those that are more important or that are more commonly used. But it might be the case that you want to specify a very accurately a parameter in the network. And since Scipion is not giving you that parameter here, you can use these extra params to provide the real flag that should be passed to the CryoDragon program, as if you were running it in the command line with the value you want. All these parameters will be passed to CryoDragon program. And lastly, we have the analysis tab. So this analysis will determine whether you want, for example, to analyze the last epoch you have trained, which usually is what you want because it's the one that you're going to be using later on in the workflow, or if you want to analyze a selection, and also how many volumes you want to generate from the conformational landscape CryoDragon has estimated. So this gives you an initial idea of the conformational states you have in your landscape. By default, we create 20, but you can create more or less number of them. And then this will create a set of volumes in a Scipion, as we will see now. Once you are happy with your parameters, you click on execute. And once the protocol has finished, you will get two outputs. First, the CryoDragon particles. Let's open them. And as you can see, it's very similar to the Cernic particles. But here, now your setFlex has a smaller vector, which are these 8 components estimated in the latent space of the network of CryoDragon, needed to recover the specific state for this particle. And also you get a set of 20 volumes, which include all the different maps that we have sampled uniformly from this landscape CryoDragon has estimated. So this, if you open this map in Chimera using the Chimera option from Scipion, you can get an initial idea of what is going on with your states. However, this is not the only way you have to explore the landscapes, and we will see later how to use the interactive tools to go in real time into the landscape and how to really extract different conformational states. And last one is the head seeder. Head seeder, as we said before, is very similar to CryoDragon in the sense that it's estimating also CryoEM densities and maps, but it's doing it in a slightly different way, in such a way that you are not only training the network to do reconstruction, but also to do other things in order to get better maps and better landscapes. When you go into the form, you will see that it's very similar to the Cernic one, but you have some extra parameters. Of course, if you go to the input tab, you need to provide the particles, and you can provide here a starting volume or reconstruction mask. These parameters are not mandatory, you can leave them empty. The idea of the starting volume is to use the network in refinement mode. So it's like, I am giving you already my map, which I have computed, for example, with Ryan or CryoSpark. I like it a lot. So I want you to use this map and refine it to get all the different states present in the dataset using the neural network. If you don't give a map here, then the network is like CryoDragon. You will train a heterogeneous reconstruction from the very beginning. And then you have the reconstruction mask, which is a mask with zeros and ones, but this is slightly different to the Cernic one. So here 0 means I don't want you to reconstruct anything in this area, and ones means I want you to reconstruct something for this box. So for example, if I want to reconstruct here the whole box of the volume, I need to give a mask that is full of ones, because I want to reconstruct everywhere. But if I give, for example, a sphere that is put inside the box, then I will only reconstruct my protein inside this sphere, and everything that is outside won't be reconstructed. So this allows you also to do focus reconstruction in different regions, or even excluding, like for example, nanodies or regions that you don't really want to reconstruct when you are doing all this heterogeneous analysis. Latent space dimension is similar to the case of CryoDragon. Usually you put here a number between 8 and 10, and it should be enough. In the network tab, you have an extra option compared to the Cernic, which is fine-tuning a previous network. So if you have trained a head seeded and now you want to retrain it using the previous network, but with different parameters, you can provide it here. In the cost function, we have an extra cost function, which is the mean square error. This mean square error is the one we are using by default in the head seeded. You can also use correlation of the Fourier phase correlation, as in the case of the Cernics, but usually this MSE will give you better results. And then in the output, is similar to the one of CryoDragon. You can decide here if you want to apply some kind of filtering to the output maps. By default, you don't want to do it because you want to see the maps at full resolution. And also you can determine the number of maps that will be decoded from the conformational landscape in a uniform way to give you an initial idea of what is going on with your maps. Once the protocol has finished, you will get your set of particles flex, which includes all the information, as we have seen before, of the head-seated network, how to cover state, and so on. And also your volumes, which, as in the case of CryoDragon, you can open a Scipion using either this view or Chimera, and it will give you an initial idea of what is going on with your conformational landscape. But as we explained before, you can also use the interactive tools in FlexUtils to explore in real time the conformational landscapes. So this is all. We have learned in this video how to use some of the tools provided in the Flexibility Hub to estimate conformational landscape from particles. In the next video, we will go into how to use consensus, how to use the interactive tools to explore the landscapes, how to further analyze all these different conformational states estimated by the Sony 3D, CryoDragon, or Head-C. Thank you so much for listening.